Good morning and good afternoon, colleagues. We are all cognizant about the progress of 5G technologies, especially decoupling, softwareization, and virtualization, and how those technologies are shaping 5G infrastructure design. Hi, I am Diman Chaudhary. Today I'll discuss about the issues of 5G synchronization and how to address it, especially when it comes to virtualized and decoupled environment. Before we delve further into this, let's start with some fundamentals, which will help us better understand as to why synchronization is so important for 5G. For this, we need to understand two distinct technologies. The first one is FDD or frequency division duplex, and the second one is time division duplex or TDD. Perhaps many of us are conversant on this subject, yet I thought it would be good to just brief over it so we can better understand as to why time synchronization is so important for Fronthaul design. So why FDD and TDD matters at all? Well, for FDD, download and upload occur at the same time at a different frequency in the same channels, as you can see. Whereas in TDD, upload and download are done in different times, and that's an important point. Different time, but in the same frequency band, as you can see. So what's the benefit of TDD? In comparison to FDD, TDD provides improved spectrum efficiency and ability to upload and download capacity on demand. Also, TDD hardware cost is very low comparison to FDD. However, to utilize spectrum more efficiently, all TDD network must synchronize. This brings us to this two distinct questions. The first question is, what is synchronization? And the second question is, why it is important for 5G network design. To better understand synchronization, let's take an example of communication between base station and end user. In here, uplink and downlink communications for a TDD network are happening in the same frequency but at different time. However, in the same scenario, if we have two end user for the same operator, let's say, and they are communicating at the same time in the same communication path, and their upload and download communication path are not synchronized, then upload or download doesn't matter from one communication path will interact with upload or download of the other user communication path. As a result, it might cause network capacity issue as well communication failure. But if we have aligned upload and download communication path for both user, we may not have this kind of issues of network capacity and communication failure. And this brings us to the important question that we asked before. Why is synchronization is so important for 5G network? Now, we talked about spectrum efficiency. There are other benefits. So spectrum efficiency is the first one. The second one is higher speed and better coverage. And the third one is the dynamic bandwidth allocation, as you could tune up download and upload path of communication based on network demand. And these are a couple of benefits that the synchronization provides. So how is synchronization achieved? For a mobile networks, synchronization refers to parameters that ensures send and receive data at the same time for in-network and adjacent networks in order to avoid interference. For a successful communication in TDD networks, these parameters are important and need to be agreed upon. So there are three distinct parameters. The first one is common phase clock reference, and the second one is timing reference, and it happens at the beginning of the frame. And the third one is common frame structure and format. As you can see, out of the three requirements of synchronization and how it is being achieved, the first two refers to time synchronization. Thus, it is more important to consider time synchronization while you are designing 5G network. In fact, you should be considering this before designing 5G network or during the design of 5G network so that you can plan accordingly, right? For time synchronization in 5G Fronthaul, we could start with ITU-T recommendation G.8271.1. This standard was originally developed for LTE and since amended for 5G, but work is still ongoing. In this standard, as shown in this diagram, there are 9 hop counts from grandmaster to the RRH or radio remote head, and up to 5 hop count for boundary clock deployment from the grandmaster. Between the RRH, a radio remote head or radio unit, between them, the time error tolerance being specified is less than 260 nanoseconds. An end-to-end network should be not more than 1.5 microsecond, but in deployment, less than 1.1 microsecond is preferred. Let us understand how ITU-T recommendation G.8271.1 applies to various 5G Fronthaul configuration, specifically to split option scenarios. We'll explore 5G split option next, but for now, let's consider how ITU-T recommendation G.8271.1 time error budget is applied to connectivity between DUs, distributed unit, and the RUs, radio unit or radio remote head. Here you can see RUs that are connected to the same DUs having 130 nanoseconds between them as a allowed time error budget. In a MIMO or transmit diversity setup, G.8271 specified internal equipment TAE up to 65 nanoseconds. And for radio unit to radio unit that are not connected to the same DUs, between them, time error budget is considered should be less than 260 nanoseconds. We talked about different split options available in 5G Fronthaul design. There are 8 possible split options in 5G Fronthaul, option 1 to option 8. In this diagram, different split options are shown with radio protocol stack. The radio unit comprises radio frequency layer and lower PHY layer, whereas upper PHY to HRLC of the radio protocol stack are processed within a distributed unit or DU, and the rest PDCP and RRC is processed within central unit or CU. The entire realm of RU, DU, and CU is known as GNB or 5G New radio base station. The communication between the radio unit and the distributed unit is done through CPRI, ECPRI, or Radio over Ethernet, or ROE. Please note, 5G Fronthaul network design concept is still evolving, continually augmented by contribution from some of the important industry forums, and those are OpenRAN or ORAN Alliance, OpenRAN project of Telecom Infrastructure Project, OpenRAN Policy Coalition, GSMA Association, GSA, and Small Cell Forum or SCF. So going back to our discussion about the split in 5G Fronthaul, one of the biggest challenge of 5G Fronthaul deployment is synchronization, specifically time synchronization, as it would be applied to virtualized 5G environment. A better way to deploy time synchronization would be to use a combination of various time sync mechanism. For example, SyncE can be extended from RU to DU and use P2P client in the DU environment along with some of the products like GM200, which could be either used as a grandmaster reference clock or boundary clock, as well as timing modules, right? And this timing module on the RES 360 and RES 720 that I'm referring here, this module provides PRTC input for either 1 PPS or 10 megahertz, and those input can be directly given to the circuitry within the radio unit as well as in the DUs, right? However you would like to implement them. So if you are putting within the radio unit and you would like to have a P2P slave in there, you could create an embedded board with RES 360 or RES 720, a P2P board, and then put the RES 360 as a PRTC input or clock input for the P2P the hardware or embedded module, right? Same you could do for DU. If you are, for example, if you are putting a NIC cards inside the DU server, NIC cards, and that NIC card may bring a boundary clock, right? And that boundary clock can use RES 360 within it, or as a standalone within the box and providing the clock. So if you have the RES module like this and you have the NIC card, you could bring the clock input from the RES module to the NIC card, right? And that will in turn provide the synchronization to the DU applications, right? So that's one way to do this. It's very cost effective. You could create a TSN environment as well, and as I mentioned, you could use the SyncE underneath for synchronization. If you cannot carry the PPS from radio unit or from the radio tower all the way to DU, you could use a SyncE between them at PHY level to synchronize the network, right? So we are applying the concept of time error tolerance to OpenRAN 5G environment. OpenRAN concept, it's actually a collective work of OpenRAN Alliance or ORAN Alliance and Telecom Infrastructure Project, which provides a decoupling concept. It defines a decoupling concept of hardware and software, and then specifies an API that will connect with OEM infrastructure, right? Operation, administration, and management infrastructure. So depending upon the split, an operator can create a virtualized environment for OpenRAN, vRAN, as well as the CRAN environment. So if it is in option 8, you create a vRAN environment, and if it is a option 7, you could use DU and RU and create your virtualized OpenRAN environment. So here we are taking the example of 7 option and 8 option split. Time error budget between the two RR range, as you can see here, is 260 nanosecond. But you have to note that this RR range are connected to 2 different DUs, right? If they are connected to the same DUs, it would be 130 nanoseconds. So to achieve such an accuracy, you need a certain product like RES 360 and RES 720 I mentioned here. So RES 360, the difference between RES 360 and RES 720 is that this is a single band and this is a multi-band. So for example, it has an L1 and L5 capabilities for GNSS. So in case of if one frequency fails, it will go into another frequency, as well as it provides a smart GNSS assurance capabilities. So it can detect jamming and spoofing and so on and so forth. So you're getting some form of resilient time. Then you can connect a bullet antenna 360 antenna to the RES 360 or RES 720 module, and that in turn can be integrated into your RU or RREU or RRH embedded module, providing internal clock to it, right? So as you can see, that the Trimble product line provides you a very cost-effective way. I'm talking about extremely low price that you could use RES 360 and RES 720 for your TCO model. You could build a time synchronization network with this product, as well as a boundary clock or grandmaster. Traditionally, a lot of vendors kind of control this market of grandmaster and boundary clock, and they have raised the price for this kind of product. But Trimble provides very cost-effective product lines, boundary clock and grandmaster, for you to use in your virtualized environment. You can connect with the DUs. All this DU stack can be connected with a single grandmaster, or you could use a boundary clock for each of them, depending upon how this DU setup is, right? You can also put Trimble P2P client, and if there is a hardware NIC card in there to provide hardware timestamping, now you can get a better accuracy using this P2P client and provide that accuracy to the applications within the DUs, right? So achieving the 1.5 less than 1.5 microseconds or less than 1.1 microsecond time tolerance for your entire network is not an issue. So just wanted to show this, how you could create this time synchronization and be within the time error tolerance of 5G, OpenRAN, vRAN, and CRAN environment with the Trimble products solutions within this diagram. We discussed about the 5 boundary clock hop counts as per G.8271.1, right? Here is a tier 1 example, US tier 1 example. As you can see, they have only used a max boundary clock hop count of 2 nodes, right? And they are using GM200 as a boundary clock with the DUs. You could use even an embedded module within that, and then they're also having an embedded RAS module within the DUs, some of the DUs. So the choice you have with the RAS 360 and 720 is that you could either use it inside the RUs or DUs, depending upon how you would like to build your network and solutions, right? And with GM200, now you could literally connect up to, let's say, 32 DUs to one single grandmaster, or 32 CUs to one single grandmaster, how you would like to create your network, and you can still be within the time error tolerance being specified. Some of the standard that you should also take into context are ITU-T recommendation 8275.1 and ITU recommendation 8275.2 for coordinated PRTC. And this standard basically emphasize recommendation 8271.1, and I would suggest that you use one grandmaster per CU, right? And parsing clusters you create end-to-end network less than 1.1 microsecond with the time budget, right? So these are some of the parameters need to be considered, and it is being considered by one of the tier one provider. So I just thought of highlighting this and how this solutions was created by Trimble product line. I referred earlier creating a single time sync cluster per CU, and then connecting a grandmaster here in Trimble's GM200 to the CU. But one thing to note here is that the maximum hop count should be between the DUs and the CUs for boundary clock 223 node. Now, if you are connecting the DUs with a DCSG type of device to aggregate, DCSG puts a boundary clock in there. So it depends how many DCSG you are connecting to aggregate DUs. But please note that the DUs that are connected to the DCSG do not need DCSG to connect to the CU. It can either directly connect to the CUs depending on the port count available in CUs, or you could put L2, L3 switches in there. If you have the need for MPLS, then of course you need a specialized switch, but generally it's L2, L3 switch will suffice. And in that case, you could use a GM200 boundary clock to the L2, L3 switch and then provide the time synchronization that way. The only need for DCSG comes in because this product has an ASIC plus a P2P module with a PRTC input to it. So it provides a boundary clock as well as L2, L3 and MPLS capabilities within that switch. But it is expensive and limited by the ASIC provider, because only so far I know single ASIC vendor is capable of providing DCSG kind of environment, because the interface between the P2P and the ASIC is a sync interface, and that's few ASIC vendor can able to provide, and that's the reason it is very limited, and its price point is much higher than you can buy a standard L2, L3 switch for. So if you are connecting with the GM200, you could rather use an L2, L3 switch than DCSG. There is no point of buying an expensive product to create the same solution that you could create with GM200 and the standard L2, L3 switch, right? The same concept that we talked about earlier applies to a macro environment as well. There is, as far as the sync cluster goes, there is no difference between what we discussed, having a single sync cluster per CU. There is no difference here as well. DCSG, as I mentioned, you could replace with an L2, L3 switches and connect a GM200 as a boundary clock to L2, L3 switch. Only thing that's new here is the embedded timing module that you could put in the picocell environment, right? So this same concept applies. You have the picocell circuitry, and you use RAS module as the PRTC input to the picocell circuitry. Similar to here in the DU, you have the DU circuitry, and then you could use and RAS module as a PRTC input to the circuitry directly, or to a P2P module and then to the circuitry, and then this device will be able to synchronize properly to the network. So I refer to 5G telecom cloud. The diagram here shows a type of network that is designed for 5G telecom cloud. In fact, you will see 5G telecom cloud will become how future operator design their network. And here, things to note is that the data centers is getting decentralized to edge aggregation as well to far edge. So we talked about time sync cluster, creating time sync cluster, but one thing to note that the time sync cluster now is within the far edge. All the concept that we talked about comes into the far edge. Here you have the DUs and the CUs, right? So if you are creating a multiple of far edge cluster, and depending upon how many CUs here, per CU should have one GM, and the CUs will have a multiple of DUs, and per DUs it should be recommended that you have 3 RU, although you could have up to 24 RUs connected to it, but it is recommended that you have 3 RUs in there. So in terms of putting the RAS, you could put it the RAS 360 or 722 RIU or RU, as well as to the DUs and the GM200, depending upon how you created your cluster. It could be a grandmaster connected to the CU, or it could be a boundary clock connected to the DU. I have referenced some of Trimble's time and frequency product, specifically RAS 360, RAS 720, Bullet 360 antenna, as well as the GM200. And hence, I thought of taking this moment to introduce Trimble's time synchronization portfolio for the audience. The first one we talked about, it's a single band timing module that provides PRTC input in the form of PPS and PP2S. The second one is ICM 360, which provides PPS, PP2S, and in addition 10 MHz input. Both of these products can be used in a cell site router, radio unit, DU, CUs, and Node V. RAS 720, I have referenced it several times during 5G Fronthaul network design discussion. You could use this in the cases where resilient timing is required. This product provides multi-band capability L1 and L5. And this particular product also supports anti-jamming, anti-spoofing capabilities. It provides PPS and programmable 10 MHz clock input. When I'm talking about programmable 10 MHz, I'm referring to sine wave and square wave capabilities. This product also can be integrated into cell site router, radio unit, active antenna unit, DU, CU, Node B, and so on and so forth. The next product is a discipline clock. Mini TGG I'm referring here is a discipline clock. The current product provides 1.5 microseconds for 7-minute holdover. So in case of a GNSS PRTC failure, you could use the holdover mechanism to guarantee PRTC for the network. The future product will support up to 24 hours of holdover. So if you are looking for a very resilient mission critical infrastructure and looking for resilient timing solutions up to 24 hours holdover time, our future discipline clock would be ideal for you. And you can use it also alongside timing module to various different solutions. The bullet series of antennas are high gain single band or multi-band multi-constellation hardened antennas. Hardened means you could use them in outdoor, and you could use this product in conjunction with the timing module, as well as they could be used for boundary clock and grandmasters. Equitam 360 is a smart antenna. It has a built-in GRU, meaning GNSS receiver unit. So in cases where you have a space constraint for your design, you rather opt for a smart antenna like a 360 and get the PRTC input in the form of PPS and use it in your design. TS200 is a network time protocol server which you could use in a data center environment where you need millisecond level accuracy. GM200 is a grandmaster. It also has capability to be a boundary clock and provide P2P capabilities. So it connects to the antennas, bullet antennas, and provides P2P connectivity to your network. Right? It also have capabilities to provide PPS output. So you could use this kind of products as a grandmaster to your far edge aggregation, wherever you need 32 client or so to be supported. You could use GM200. You can also use it as a boundary clock with the DUs or like a L2 L3 switch we discussed earlier to provide solutions for your 5G network design. I hope you have enjoyed the discussion here for 5G sync plane design. If you do, please do not forget to click the like button in LinkedIn and YouTube. Also, you could email me, diman_chaudhuri@trimble.com. And thank you for your time.